Hi, this quest is to take arguments that would be arguments to the dyadic transpose function and see if the left argument is valid given the right argument. I have prepared some test left arguments and some test right arguments. We can use the example function that is outlawed to try these out. What's happening here is that we have a lambda, a function, and we set up an error guard that says if any error happens, then we return 0, meaning it's an invalid left argument. Otherwise, we're going to return 1. We do that by actually trying to do the transpose, discarding the result, and then returning 1. So if this worked out without giving an error, then we return 1. And so we can see that in this 2x5 table of test cases, the entire top row are the ones that are valid, and the ones at the bottom row are invalid. Now, the actual content of the right argument, and even the size of the, or shape of the right argument, isn't irrelevant. The only thing that is relevant is how many dimensions it has, and that has to match up with the left argument. So let's try putting these next to each other. We put the left arguments next to the right arguments, but we are going to take the shape of the right argument. Oh, sorry, it should be the shape of each one of the right argument. Here we go. Okay, so we can see here that in order to be valid, then the left argument must have the same number of elements as the shape of the right argument. So that's one criterion. The other criterion is that the left argument must enumerate x's that we want to map the existing x's to. And the x's had to be consecutive, counting up from 1, but in any order. And we allowed duplicates. So we can see some example of valid ones. This is, of course, just a permutation vector. So here we're just changing the order of the x's. This one, we are mapping two x's, the first and the last x's, to x's 2. Here we are mapping both x's to a single x's. Down here, this is almost okay, but we're not mapping anything to the first axis, and there has to be a first axis in the result, so that's invalid. And here the problem, the left argument is valid, but only for a rank 2 array, a 2-dimensional array, but the actual right argument has 3 dimensions. Over here, we're not using integers, so that's invalid. You can't enumerate the x's with fractional indices. Here we have too many, and here we have too few, because the right argument is empty. It has length 0, but it's empty along that one axis that it's empty along, but we don't have any axis on the left. We could also combine this with the tally of the x's, and this just gives us the count, the number of dimensions in the right argument. So we can see here that this is a 0-dimensional array, but we're trying to pair it up with a list of x's that has 1 element. So we're trying to map an axis that doesn't exist, just as an example. Okay, now let's get started. So there are 2 parts to this. There is the part about being a kind of permutation vector, but possibly with duplicates. And then there's the part where the number of elements on the left has to match the number of dimensions on the right. The first part, whether or not the argument is a permutation vector, possibly with duplicates. So these are all our left arguments, and we're trying to compute something on each one of them. So we have the lambda and the each. Now, again, two parts to this subproblem. There's the permutation part, and then there are the duplicates part. The easiest thing to get rid of is duplicates. That we can just do with the unique function on the right argument. So this gives us rid of all the duplicates. And then we have to check whether or not it is a permutation. For that, we have to go explore the grade primitive a bit. So this is grade up. Let's try some argument for that. What grade does is it returns the indices that you would need to use in order to sort. So what this is saying is, in order for this to become sorted, we need the third element first, then the first element, then the second element, and finally the fourth element. We're not going to sort, but what is interesting here is that if we grade again, this is already a permutation vector, and asking for the indices that would sort a permutation vector is the same thing as asking instead of which element should I take in order to get things sorted, then where we're getting instead, where should I send this element in order to get things sorted? So if we try this, it says send this element to the second position, send this element to the third position, this one goes to the first position, and this one stays in the fourth position. Why is this relevant? Well, if actually we already have a permutation vector, so this is a permutation vector because it contains all the numbers from 1 to its length, 4, and we grade that. So this gives us, again, which element should we take in order to get this to be sorted. So we want element number 2, element number 4, element number 1, and element number 3. Now if we do the grade again, which is the inversion of the permutation, notice that we get back to where we were before. Well, makes sense. If this is invert a permutation and we invert the permutation twice, we should get back to where we were. That means we can write a function that checks whether or not a given vector is a permutation vector by comparing the original vector to the grade of the grade. So we can write this as the argument matches the grade of the argument. And we can try this. This is a permutation vector. This is not a permutation vector. The only thing we're now missing is that we want to look at the unique elements, not just all the elements. If we try this first on X, oh, right. Some of the elements of X are scalar. But we can fix this by reveling the argument. Right, so here we have some that are valid according to this criterion, and some of the invalid ones are also valid for this criterion. It's going to fail the other one, but some of the valid ones are invalid, marked as invalid because not being permutations. Let's look at X again, and we can see that that's because they have duplicates. Now let's try to compare with the uniques instead, and we don't need to revel anymore because unique itself would revel if the argument is scalar. This works. We can beautify this a little bit and make it a little bit more efficient. We only need to compute the unique elements once. Let's assign those to u, and then we can just use u. Right. This takes care of the one argument criteria, which is that the left argument must be a permutation vector, although it is allowed to have duplicates. The other criteria is that it had to match its length to the length of the shape of the right argument, that is, the rank of the right argument. Now let's include the right argument. We want the length of the left argument to be equal to the length of the shape of the right argument. This worked right away, but we can beautify this as well. Notice how the equality is between two lengths. This calls for the over operator, which preprocesses both arguments to a function with some other function before the main operation is done. Right? Now we see that we have two arguments being given to this main function, but one of them is being preprocessed by the shape. Then we can use the beside operator, which preprocesses only the right argument to the main function with a preprocessing function. And finally, we just have a single derived function, which is wrapped in a defn, lambda. That means we can just take away the wrapping. This is the other part. This checks whether the left argument has equal length to the shape of the right argument. Now all we need to do is combine the two criteria. We want this one to be true, and we want the unique elements matching the grade of the unique elements, which are the unique of the left argument. This is our solution. We can give it a name. And now we can write using this name. Thank you for watching.